We're going to be covering 3.3 through 3.4, and this begins with the mass relations in chemical formulas. So for example, water is 11.1% hydrogen and the remaining 88.9% oxygen. So that would be the mass relationship of the hydrogen and oxygen in water. Well, from that knowledge, we can calculate the empirical formula, meaning we determined that that formula was H2O. Empirical formulas are the smallest whole number ratio of elements in a compound, and more often than not, they're the actual formula. We'll learn about calculating empirical formulas, and then with one more piece of information, we can calculate if they are the actual formula or some fraction of it. Then we'll talk about the relationships of mass and chemical reactions. We'll learn about balancing chemical equations and some common additional information that shows up in chemical equations. Let's get warmed up with a little bit of review. We're first asked, what is the formula of the cyanide ion? Well, normally "ide" means a single element all by itself, but this is one of those two polyatomic ions with an "ide" suffix, and that's going to be carbon and nitrogen with a -1 charge. What about sulfide? Well, there is a sulfur element, and sulfur with a expected -2 charge. And we get that by looking at the position of sulfur in the periodic table. What about nitrate? Well, eights and ites have oxygens, and I would ask, how many oxygens does nitrate have? Nitrogen is in period 2. It's part of that 7. Remember period 2 in group 7A? And so that means that nitrate has 3 oxygens. I also need a charge, and that comes from the bonding number of the non-oxygen. The bonding number of nitrogen is 3, but it's one of our 2 exceptions where you reduce that bonding number by 2. And so 3 minus 2 is 1, and that's where we got the charge of -1. So when it comes to a polyatomic ion, there's 2 things we need to determine: the number of oxygens and the charge. Let's name this compound, and we have 2 types of compounds. We have molecular and we have ionic. And since this compound begins with a metal, we know it's ionic. What's the name of that metal? Barium. Does barium get a Roman numeral? No, it's a main group element, so it's always constant, and so just barium. Name of the anion? Well, nitrogen all by itself is nitride. Again, the "ide" suffix means a single element in most cases. And what's the name of this compound? Well, again, I see a metal, so what's the name of that metal? Iron. Does iron get a Roman numeral? Yes, it does, so we'll leave an empty spot behind for it. And now the name of the anion, oxide. Again, single element, oxide, and each oxide carries a charge of -2. 3 -2s is -6. Why was I interested in this? Because that tells me what my total positives are. And when I divide that by that there are 2 irons in this compound, I see that each one is +3. For iron, Roman numeral 3, oxide. Let's name this compound. I see a metal and a polyatomic ion. Both of those tell me this is ionic. What's the name of that metal? Cobalt. Does cobalt get a Roman numeral? Yes, it does. Again, we'll leave an empty spot behind for it. Now the name of the anion. Well, how many oxygens does phosphate have? Well, phosphorus is not in the 7. Remember, that's period 2 in group 7A. And so phosphate has 4. So this is phosphate. Now, what's the expected charge on the phosphate? Well, the bonding number of phosphorus is 3, and it's not one of our 2 exceptions. So phosphate is -3. There's only one phosphate, so that -3 is balanced by +3. And hence this is cobalt, Roman numeral 3, phosphate. Again, I see a metal, so this is ionic. What's the name of that metal? Sn is tin. Does tin get a Roman numeral? Yes, it does, so we'll leave an empty spot behind. Then the anion, again, that's oxide. So we have tin, Roman numeral, oxide. Each oxide has an expected charge of -2. 2 -2s is -4, which must be balanced by +4. Or tin, Roman numeral 4, oxide. Again, if your metal has a constant charge, it's just the name of that metal, but if it has more than one charge, we have to give that charge as a Roman numeral as part of the metal ion's name. And what's the name of this compound? Well, what's the name of that metal? Silver. Does silver get a Roman numeral? No, it's actually part of the periodic table where there are a lot of elements that have a Roman numeral, but it's actually part of that little triangle. Remember that triangle? And that means silver's always got a constant charge. It's +1, so just silver. And now the name of the anion, sulfide. Again, a single element gets that suffix of "ide." Ites and ates, the ones with the T's, they get the oxygens. Okay, what's the name of this compound? Well, I see a metal and a polyatomic ion. What's the name of that metal? Potassium. Does potassium get a Roman numeral? No, so just potassium. Name of the anion? Well, how many oxygens does phosphate have? Phosphorus isn't in the 7, so phosphate has 4. This is one less for phosphite. Altogether, potassium phosphite. Again, I see a metal, so it's ionic. What's the name of that metal? Lead. Does lead get a Roman numeral? Yes, it does. Name of the anion, nitride. So lead, Roman numeral, nitride. What's the expected charge on a single nitride? Well, nitrogen wants to gain 3 electrons to be like neon, so -3. 4 -3s is -12. -12 is balanced by +12. When I divide that +12 by the 3 leads, each one is +4. For lead, Roman numeral 4, nitride. I see a metal and a polyatomic ion, so I know this is ionic. What's the name of the metal? Manganese. Does manganese get a Roman numeral? Yes, it does. Name of the anion? Well, it's nitrate or nitride or hypo or per. Let's just ask how many oxygens does nitrate have? And nitrogen is in the 7, so it has 3, so that is nitrate. I need the charge on each nitrate to determine the charge on the manganese, and the charge comes from the nitrogen's bonding number. Nitrogen has a bonding number of 3, but remember, carbon and nitrogen are our 2 exceptions, so we take that bonding number and reduce it by 2. So 3 minus 2 is 1, or -1. 2 negative 1s is -2, and hence this is manganese 2 nitrate. And now let's put together the formula of cobalt-3 sulfite. Well, cobalt is CO, and the 3 tells us the charge. Sulf, anything has sulfur. Ates and ites also have oxygens. And we use the position of sulfur in the periodic table to ask how many oxygens does sulfate have? And sulfate has 4. And so sulfide has 1 less, or 3. I get that charge from the bonding number of the sulfur. The bonding number of sulfur is 2, and it's not one of our 2 exceptions. Remember, our 2 exceptions are carbon and nitrogen, so -2. Okay, so 3 and 2, there's bonding number 3, bonding number 2, least common multiple is 6. That says +6, which is going to take 2 cobalts. It's balanced by -6, which takes 3 sulfides. Okay, I see a metal and a polyatomic ion. What's the name of that metal? Zinc. Does zinc get a Roman numeral? No, it's also part of that triangle. And so just zinc. And the name of the anion, well, this was one on the other list, meaning we can't predict its name. And I hope you recall that it's oxalate, or zinc oxalate. And what's the formula of chromium-3 hydrogen phosphate? Well, chromium-3 says Cr+3. Hydrogen phosphate, so we have hydrogen, phosphorus, and some oxygens. How many oxygens does phosphate have? And phosphorus isn't in the 7, so phosphate has 4. I get the charge from the bonding number of the phosphorus. The bonding number of phosphorus is 3, and this would be -3, except for that hydrogen means that it wasn't able to get rid of steal all 3 electrons, it was only able to steal 2. Remember, you have 3 negatives from 3 hydrogens that you stole 3 electrons from. Using those bonding numbers, we get the formula Cr2 HPO4 3 times. Again, bonding number 3, bonding number 2, these come multiple of 6 as positive 6. There's your 2 chromiums. Is balanced by negative 6. There's your 3 hydrogen phosphates. Okay, this is an acid, so let's put our thumb over the hydrogen and ask, what's the name of that ion? Well, how many oxygens does bromate have? 3. So BrO3 is bromate. And 8 ions come from ic acids. So bromic acid. Remember, 8 ions came from ic acids, and 8 ions come from us acids. And why no hydro? Because there's oxygens. Hydro would be a binary acid, so just H and Br would be hydrobromic acid. Now the formula of aluminum dichromate, well, aluminum's a +3 ion. I get that from the position of aluminum in the periodic table. It wants to lose 3 electrons to be like neon. Dichromate, that's one of those polyatomic ions on the other list. And now, those charges are bonding numbers. Bonding number 3, bonding number 2, these come multiple of 6. And what's that 6 tell us? Positive 6, which takes 2 aluminums, is balanced by negative 6, which takes 3 dichromates. Another ionic compound to name. What's the name of the metal? Iron. Does iron get a Roman numeral? Yes, it does. We'll figure it out in a moment. And now the name of the anion. Hydroxide. This is the other of the 2 polyatomic ions that has the "ide" suffix. And you may recall that both of them had 2 elements and a -1 charge. So hydroxide is -1. 3 negative 1s is -3. So that iron is +3, or iron Roman numeral 3 hydroxide. And now, what's the formula of potassium nitride? Well, potassium's from group 1, so K+1. Nitride, nitrogen wants 3 more electrons to be like neon, so -3. There's our bonding numbers. Bonding number 1 for the potassium, bonding number 3 for the nitrogen. Least common multiple of 3 tells us +3, which takes 3 potassiums, is balanced by -3, which takes a single nitride. Name this compound. Well, what's the name of that first element? Selenium. Well, if selenium is a nonmetal, this will be molecular, but if it's a metal, it's ionic. And selenium is a nonmetal, so that means it's molecular, so we use the prefix system. So selenium tetrafluoride. Now note, if selenium was a metal, it'd be ionic, and this would either be selenium fluoride or selenium Roman numeral 4 fluoride. Totally different names than it being molecular. And the monodi, tris, tetras are only used in molecular compounds. Okay, what's the molar mass of an element? Well, there's 2 definitions I like. One is, this would be a mass in grams equivalent to the atomic weight. So just grab that number and apply the units of grams per mole. And the other is, this would be the mass that would contain Avogadro's number, the mole number of that element. And the molar mass of a compound is the sum of the masses of the elements that make it up. And the molar mass of 10, okay, well, let me grab my periodic table, 10, Sn, and I see 118.7 grams per mole. For the molar mass of carbon dioxide, well, you gotta love molecular names, the formula just jumps right out at you. And for a compound, you need that formula first. And now I see how the mass contribution of 1 carbon, so 12.0 grams per mole, to oxygens at 16.0 grams per mole, or 44.0 grams per each mole. Now for the molar mass of 10,2-phosphate, I have an ionic compound, so I have to put a lot more work into coming up with a formula. So first, 10,2, that's Sn plus 2. And then phos, anything contains phosphorus. 8s and ites also contain oxygens. And I look for the position of phosphorus in the periodic table to tell me how many oxygens does phosphate have. Remember, it's either 3 or 4. If the non-oxygen is in period 2 or group 7A, looks like a 7, it's 3. Everybody else it's 4, and phosphorus is one of the others, 4, 4. Next for the charge, that comes from the bonding number of the phosphorus. The bonding number of phosphorus is 3, and it's not one of our 2 exceptions, so negative 3. All right, there's our bonding numbers. Bonding number 2, bonding number 3. Least common multiple is 6. Now what's that 6 tell us? Positive 6 is balancing negative 6. So positive 6 has 3 of these 10s, negative 6 has 2 of these phosphates. And now that we have the formula, we can come up with the molar mass. We have a mass of 310, so 3 times that 118.7 grams per mole. 2 phosphorus, each at 31.0 grams per mole. And how many oxygens? Well, 2 times 4 for 8 oxygens at 16.0 grams per mole. That all adds up to 546.1 grams per mole. Okay, now we're asked for the mass of 12.5 moles of carbon dioxide. Well, step 1, first we're using our units. And if we hadn't already come up with a formula of carbon dioxide, we might do that as a preliminary step. We're ready for step 1. What are we after? The mass, so grams of carbon dioxide. Step 2, we're looking for a number with a single unit to start the calculation with. And I'm sure you knew that was 12.5 moles of carbon dioxide. And here comes the beginning of step 3, out of moles of carbon dioxide. And getting this far should be pretty much a no-brainer. And now can we go straight from moles of carbon dioxide to grams? There's our most common calculation in all of chemistry. Yes, we sure can. And we also determined the molar mass earlier. If not, we'd be doing it now. 1 carbon at 12.0 grams per mole, 2 oxygen at 16.0, or 44.0 grams per each mole. So multiply the 12.5 by the 44 for 550 grams. And now calculate the number of moles of formula units contained in 1 kilogram of 10,2-phosphate. Okay, well, we're using our units, and if we hadn't have come up with the formula of the 10,2-phosphate in a previous problem, we might be doing that as a preliminary step, because we need it right here in step 1 when we write equals moles of 10,2-phosphate. Step 2, we're starting with that 1 kilogram of 10,2-phosphate. And now the beginning of step 3, let's get out of kilograms. And here comes the big question, can we go straight from kilograms to moles? No, to go to moles we have to be in grams, so let's convert from kilograms to grams. And then from grams we can go to moles, our most common calculation component in all of chemistry, going back and forth between grams and moles. 1 kilogram, 10 to the positive 3rd grams, and that was 546.1 grams per mole of the 10,2-phosphate. Again, we did that earlier. If not, we can be doing it right now. Or 1.83 moles of the 10,2-phosphate. And again, we got the formula and the molar mass of 10,2-phosphate from the previous slide. And now calculate the number of atoms in each sample given below. Okay, we're using our units. Step 1, we're after uranium atoms. Step 2, we're going to start with that given 0.0010 grams of uranium. And now step 3, out of grams of uranium, and getting this far should always be a no-brainer. That's the idea of these first 3 steps to get us well on our way before we get to the challenging part. And the challenging part is right now. When we ask, can we go from grams of uranium to uranium atoms? No, there's only one way to get to a number of uranium atoms, and that's through moles. So first from grams of uranium to moles of uranium, so that we can go from moles of uranium to a number of uranium atoms. From the periodic table, we get 238 grams of uranium per each mole. And I hope you recall Avogadro's number, 6.022 times 10 to the 23rd. or 2.5 billion billion. And do note, that's 1 milligram. 0.001 grams is a milligram. That's maybe a fat piece of dust. And yet look at how many atoms are in that fat piece of dust. Atoms are truly small things. Okay, we wouldn't even be able to see that 2.5 nanograms of mercury. We'd have to have a good microscope. Step 1, we're after mercury atoms. Step 2, of course, we're starting with the 2.5 nanograms of mercury. And step 3, out of nanograms of mercury. Again, getting this far should be easy. Now comes the challenging question. Can we go from nanograms to mercury atoms? No, we're going to get 2 mercury atoms from moles of mercury. And we're going to get 2 moles of mercury from grams of mercury. So first we do grams of mercury. And then from grams to moles of mercury. So that we can go from moles of mercury to an actual number of mercury atoms. 1 nanogram, 10 to the -9th grams. Mercury has a molar mass of 200.6 grams per mole. And again, Avogadro's number per each mole. For 7.5 trillion mercury atoms. And again, I don't think we'd even be able to see that sample, but with the best microscopes. So the best microscopes can't see molecules, can't see atoms. Okay, on to new material. We're going to start with the mass relations in chemical formulas. And so I want to begin with what's called the percent composition from the formula. We may be asked, what's the percent of hydrogen in water? And so first, any percent is your subject divided by your total times 100%. Again, any percent is your subject divided by your total times 100%. I like this form of the percent equation because it's usually real easy to tell what your subject is. In this particular question, we're asked a percent by mass of gold, so this will be the mass of gold. And then our total will be the total mass of the compound. So the mass of the gold, well, there's 2 golds, so 2 times its molar mass of 197 grams per mole, over the total, and so that includes the mass of the gold and the mass of the sulfur. And I multiply that by 100%, I get 80% gold. So again, your percent by mass is going to be the mass of that element in a compound divided by the total mass of that compound. Now I wanted to start here because to come up with the formula of a compound, specifically the empirical formula, often you're given that percent by mass of each element in the compound. Well, first, an empirical formula is your simplest whole number ratio of elements in that compound. And most of the time it is the actual formula of the compound. So the empirical formula of water is H2O and the actual formula of water is H2O. But the empirical formula of hydrogen peroxide is HO, whereas the actual formula is H2O2. So do note your empirical formula is either the actual formula or some whole number fraction. Okay, so first we would analyze a compound and either be given the masses of each element in the compound, or maybe we'll be given the percent mass, kind of like we did in that last example. And then we would work backwards from that given percent mass to the actual formula of that compound. Okay, now to determine the empirical formula of the compound, well, let me take a time out. First I want to point out that this comes from experimental data, so you might not get exact numbers. Remember, exact numbers don't show up in measurements. And so, as I give an example here, 2.948 could actually be 3, and actually within 0.3%, within 3%, it is 3. Okay, so again, your first step would be to take whatever mass you're given and convert it into moles, because the mole is actually a number, and so we want that number ratio. So the mole ratio is going to give us that number ratio we're after. I want to point out that if you're given a percent, then just simply turn that percent number into grams. So if you're given 12% chlorine, well, then just use 12 grams of chlorine. Now, we need to convert each of these numbers into moles, and we want to get the simplest whole number ratio. So once they are in moles, we would divide by the smaller number of all those numbers of moles. And sometimes we're done at this point, but a lot of times we're not. And we might get a number like 1.5 or 1.33. Well, those are like the fractions 3/2 or 4/3. And so we need to clear those fractions by multiplying the whole equation by 2 or 3, whatever that denominator would be. At this point, we should have whole numbers, and if they're pretty close, then we would go with them. Again, if they're fractions, then we're going to try to identify what those fractions are. But usually by the time we're done with 2b, we have whole numbers, and these are the molar ratio, which is the atom ratio, or the subscripts in your chemical formula. Okay, let's do an example. We're told that lysine is 19.1% nitrogen, 9.6% hydrogen, 22% oxygen, and 49.3% carbon. Well, I'm going to take those percents and turn them into mass and line all those masses up along the left side of my working space. Now, the first thing we need to do is convert these masses into moles. So, using the molar mass of nitrogen, I convert grams into moles of nitrogen. Using the molar mass of hydrogen, I convert mass into moles of hydrogen. Using the molar mass of oxygen, we convert the mass into moles of oxygen. And the same thing for the last guy, the carbon. Using the molar mass of carbon, we convert from mass into moles of carbon. Now these numbers are the mole ratio. They're just what I would call ugly numbers. They're not whole numbers. And so to hopefully generate whole numbers, we're going to divide everybody by the smaller, that 1.36 moles. So again, we're going to divide everybody by the 1.36 moles. And that's going to give us 1 nitrogen, pretty close to 7 hydrogens, pretty close to 1 oxygen, a little bit more than 1, not quite 1, and pretty close to 3 carbons. So like I said, this comes from experimental data, so we might be off in just a few percent of a whole number. Okay, well we do have whole numbers here, so we don't have a step 2b, and we're pretty much done. Those numbers, the mole ratio, is the atom ratio in the chemical formula. So they become our subscripts. And there's our formula for lysine. And any empirical formula determination is going to be done pretty much the same way. Next we have a sample of an aluminum compound that contained 32.38 grams of aluminum and 28.8 grams of oxygen. What's the empirical formula? Well, like we did before, we're going to take those masses and line them up on the left. And in step 1, we're going to convert each into moles. So using the molar mass of aluminum, I convert the mass into moles of aluminum. Using the molar mass of oxygen, I convert this mass into moles of oxygen. Now this is the mole ratio, but they're not whole numbers, so step 2a, we're going to divide each by the smaller number. So we're dividing each by 1.20 moles to give us 1 aluminum and about 1.5 oxygens. So that 1.5, that's not a whole number, so that's where we're going to have a step 2b come in. So that 1.5 is like 3/2. And so to clear the fraction, we multiply everybody, so the aluminum and the oxygen, by 2. And hence we have 2 aluminums and 3 oxygens for the formula of Al2O3. And there's our empirical formula of aluminum oxide. And most of the time that is our actual formula. For an ionic compound it is always the actual formula, because the actual formula is always the simplest whole number ratio of each element in the compound. Okay, actual formulas are either the same as the empirical formula or some multiple. I gave the example earlier with hydrogen peroxide, and actually I think we're going to start with that example. Now, to determine what the actual formula is, we need to be given the molar mass of the actual formula, and then we would divide this by the molar mass of the empirical formula, and this would tell us how many times the empirical formula went into the actual formula. So I mentioned that the empirical formula of hydrogen peroxide is HO, and we're told that the actual formula of hydrogen peroxide has a molar mass of 34 grams per mole. So we're going to take that actual molar mass of 34.0 grams per mole and divide by the empirical molar mass, and the empirical molar mass is 17.0 grams per mole. So I think we're already seeing that there's 2 HOs that are going to go into this. So again, we take the actual molar mass, divide by the empirical molar mass, and this tells us how many times the empirical formula shows up. So we have 2 HOs, or H2O2. And that's the actual formula of hydrogen peroxide. So again, you take the actual molar mass, divide by the empirical molar mass, and multiply by the empirical formula. Okay, on to the mass relations in chemical reactions. Well, I think we know that the mass of the reactants are going to be equal to the mass of the products, because atoms are never created or destroyed in a chemical reaction. Now let's talk about chemical reactions and chemical equations, and essentially a chemical reaction occurs by breaking the bonds in the reactants and then reforming them into new bonds in the products. And a chemical equation is going to essentially show that reaction. So you'll have the reactant shown on the left and the new product shown on the right, and usually an arrow pointing towards the right to indicate this is what this is turning into. Now, when we have a chemical equation, then the coefficients that sit out front, this is the only thing that we're allowed to change in order to balance the equation. And again, a chemical equation has to be equal on both sides. If you start with 1,000 carbon atoms, you finish with 1,000 carbon atoms. If you start with 1 oxygen atom, you're going to finish with 1 oxygen and that atom. So again, your chemical equation needs to be balanced, meaning it needs to reflect that it's equal on both sides. Now let's go over some examples. And so here we see a carbon reacting with oxygen to form carbon dioxide. Oxygen shows up as O2. Most gases are diatomic gases. All of our molecular gases like O2, H2, N2, Cl2, essentially if you know it's a gas other than a noble gas, meaning that group 8A elements, then it's a diatomic gas. And if we think about it, oxygen wants to be bound to somebody, and so in elemental oxygen it's bound to another oxygen. Same with nitrogen in the elemental nitrogen. But anyway, so oxygen shows up in a package of 2, and so I have 1 carbon reacting with 2 oxygens, 1 packages of O2. But on the product side I see the 1 carbon and the 2 oxygens. And we'll talk about that additional information that shows up there, the S's and G's and that triangle, which is actually the capital Greek letter delta. Here's a reaction between hydrogen and oxygen. Again, do note both hydrogen and oxygen show up as diatomic molecules. And so, since the minimum number of oxygens is going to be 2, I'm going to have 2 on the right to show that balance. And since 2 oxygens on the right meant 4 hydrogens on the right, I also had 4 hydrogens on the left. And using these ball and stick models, we can easily see the number of black balls the same, number of red balls the same, number of blue balls the same. One more reaction is that between methane and oxygen. That CH4 is methane. You may have heard of methane. And do note, 1 black ball on the left, 1 black ball on the right. And essentially each methane, or each carbon takes away 1 oxygen to form CO2. So there was 1 O2 molecule. But then those 4 hydrogens got together with 2 more oxygens, 1 more O2 molecule, to form the 2 H2Os. But do note, 1 carbon on the left, 1 on the right, 4 hydrogens on the left, 4 hydrogens on the right, 4 oxygens on the left, and 4 on the right. So this is an example of a balanced chemical equation. And again, the numbers out in front of the formula is the coefficients. And no coefficient implies 1, just like x really means 1x. Okay, now when it comes to balancing chemical equations, we have a few steps. The first is to write out the formulas of the reactants and the products, and the vast majority of the time this is already done for you. So usually really nothing to do in step 1. Then step 2 is we're going to start balancing the reaction, but we begin by asking, is there any element we should leave for last? And we want to have a single appearing element like just O2 or just C or just S to be left for last. We don't want to leave C and CO2 for last because then it's changing the O as well. So we want to leave a single appearing element for last. We also want to leave any elements that appear in more than one species, meaning one reactant or product, for last. And then, essentially, going back and forth, we change the coefficients, the numbers out in front, in order to achieve our balance. Now, this is a trial and error procedure, so don't expect to do it in your head, and don't plan on getting it right the first time. Plan on breaking out your pencil and eraser. And if you have to erase a number, it told you something important. So don't plan on doing it in your head. Too often students just sit there on their hands waiting for the answer to come to them, and it doesn't come. So just get out that pencil and eraser. Okay, let's do some examples. We're asked to balance the following chemical equation, and the first one is where cyclopropane is reacting with oxygen to form carbon dioxide and water. Okay, I'm going to begin by asking, is there any element I should leave for last? And that's going to be the oxygen. That's the only element in this elemental state. And it shows up in 2 species on the right side. Okay, so I'm going to start with carbon. It's 3 on the left, 1 on the right. The least common multiple of 3 is how many I need on both sides. Whenever we balance something, we're reaching for that least common multiple. So again, we're going to put 3 carbons on the left and 3 on the right, our least common multiple. Then hydrogen. I see 6 on the left, 2 on the right. 6 is our least common multiple, meaning we need 6 hydrogens on both sides. And now I'm going to count my oxygens on the right, and I'm going to force the oxygen on the left to balance. So I have 3 times 2 is 6, 3 more is 9. Sure be nice if it's an even number, but if it's an odd number, I would write that number as a fraction. So how many O2s give me 9 O's? 9 halves of 2 give me 9. Now at this point, the equation is actually balanced. 3 carbons on the left and on the right, 6 hydrogens on the left and on the right, and 9 oxygens on the left and on the right. But I need to clear that fraction, so I'm going to multiply the whole equation by 2. You don't necessarily have to rewrite the equation. You could just scratch out the coefficients and write the new ones above them, or just erase them. Okay, one more. Here zinc is react with oxygen to form zinc oxide, and anybody I should leave for last? Either the zinc or the oxygen. I like to be consistent, so I work left to right when I can, so I'm going to start with the zincs. One on the left, one on the right, the least common multiple is 1, so I need one zinc on both sides. Then oxygen, 2 on the left, 1 on the right, least common multiple is 2, so I need 2 oxygens on both sides. Now do note, I erased a coefficient of 1. I always put my coefficients of 1 in because if I ever erase one, it's kind of a clue that somebody was already banking on that to balance. And that, of course, was the zinc. So I need to go back and change its coefficient as well. Now let's double check. 2 zincs on the left, 2 on the right. 2 oxygens on the left, 2 on the right. We're good. Doesn't take but a few seconds to double check. Okay, next we have chromium reacting with oxygen to form chromium 3 oxide. Alright, who should we leave for last? Either chromium or oxygen. I'm going to start with chromium. 1 on the left, 2 on the right. My least common multiple is 2. Whatever your least common multiple is, that's how many you put on both sides. Then 2 oxygens on the left and 3 on the right. 6 is our least common multiple, so there are 6 oxygens on both sides. And I erased a coefficient of 1, so I go and see my chromiums need to be changed as well. Now, if I hadn't have caught that, let's go back and pretend we hadn't have caught that. Let's double check. 2 chromiums on the left, oops, 4 on the right. Double checking, you would immediately catch any mistakes. Okay, so 4 chromiums on the left, 4 on the right, 6 oxygens on the left, 6 on the right. We're good. Okay, any elements we should leave for last? Oxygen this time. We only have one single appearing element. So starting with potassium, 1 on the left, 1 on the right. Least common multiple is 1. There's 1 potassium on both sides. Then chlorine, 1 on the left, 1 on the right. That's already balanced at 1 on both sides. And now oxygen, 3 on the left, 2 on the right. So what's your least common multiple? 6. So that means 6 oxygens on both sides. And we're good, right? No, we erased a coefficient of 1, and we double check. 2 potassiums, oops, 1 potassium. That's right, we need to change our number of potassium chlorides. Okay, checking again. 2 potassiums on the left, 2 on the right. 2 chlorines on the left, 2 on the right. 6 oxygens on the left, and 6 on the right. Okay, any elements we should leave for last? Either the boron or the fluorine in their elemental state. I'm going to start with boron. 1 on the left, 1 on the right. Least common multiple is 1. Then fluorine, 2 on the left, 3 on the right. Least common multiple is 6. And when I double check, 1 boron on the left, 2 on the right. Oops, I forgot my boron. So 2 on the left, 2 on the right. 6 fluorines on the left, 6 fluorines on the right. It never takes but a few moments to double check. Okay, here's that cyclopropane again, and so we saw oxygen should be left for last. In any combustion reaction, and this is a combustion reaction, cyclopropane is reacting with oxygen to form CO2 and H2O. This is what we see when something burns. Okay, we leave oxygen for last and start with carbon. 3 on the left, 1 on the right, least common multiple is 3. 6 hydrogens on the left, 2 on the right, least common multiple is 6. And then for oxygens, we count the ones on the right and hope it's an even number, but even or odd, we're going to force to balance the O2 on the left. Okay, we have for the carbon dioxide 3 times 2 for 6, and for the water 3 more for 9. So we write this as 9 halves, and then multiply the whole equation by 2 to clear that fraction. So 2 cyclopropanes react with 9 O2s to form 6 carbon dioxides and 6 dihydrogen oxides. Okay, often we're given additional information in chemical equations. The most common is special reaction conditions and the states of the reactants and products. And so the states of solids, liquids, and gases show up as S's, L's, and G's. And AQ, I believe this is the most important one. AQ refers to an aqueous solution. There's a difference between sodium chloride AQ, meaning it's dissolved, and sodium chloride S, which means that it's in a solid state. And we do include them in those parentheses, as you see in this example here. Now, special reaction conditions are often written above and or below the reaction arrow. So that heat was required, or a certain temperature, or a catalyst, or you did this under a blanket of nitrogen, or something like that. Okay, this isn't balanced, so let's let oxygen be last and start with mercury. One on the left, one on the right. Least common multiple is 1, so 1 mercury goes on both sides. Then oxygen, 1 on the left, 2 on the right. Least common multiple is 2, so 2 oxygens on both sides. And again, I erase a coefficient of 1, telling me I need to change that mercury on the right. I'm still going to double check. 2 mercuries, 2 mercuries, 2 oxygens, 2 oxygens. It never takes but a few moments to double check. That's a great habit. Double check when you're done. Okay, let's practice some of the things that we've learned here. And we're asked, what is the percent composition of silicon nitrides? We want to know what is the mass percent of silicon and nitrogen. Well, first, let's come up with the total mass of silicon and the total mass of nitrogen, because we need our subject, which is the mass of each, over the total, which will be the total masses. Again, any percent, subject over total times 100%. Doesn't matter if you're trying to calculate the percent tax you paid last year, or the percent off on your jeans, or the percent people in your family that went to college. It's always your subject over your total times 100%. Okay, so for the mass of the silicon, we had 3 silicons, each had 28.1 grams per mole, for a total of 84.3 grams per mole for the silicon. And we had 4 nitrogens, each at 14.0 grams per mole, so that's 56 grams per mole for the mass contribution from the nitrogen. Let me go ahead and add these together. So 3 times the silicon's molar mass plus 4 times the nitrogen's molar mass for my total molar mass. Of course, we could have just taken the 84.3 and added the 56.0. But now we have the 3 numbers we need. For the percent by mass of silicon, the subject here is the mass of silicon divided by the total. For 60.1% silicon. And for the percent nitrogen, we have its mass, the 56.0 grams per mole, over the total mass, 140.3 grams per mole. Multiply this by the 100% for 39.9%. And of course, we would expect that the sum of these 2 numbers should be 100%. Don't forget that simple percent equation. It works anytime you're calculating any percent. Subject, usually easy to identify, over the total, also usually easy to identify, times 100%. Chalcopyrite is the name of a mineral which contains 34.62% copper, 30.43% iron, 34.9% sulfur. What is the empirical formula of chalcopyrite? Okay, well, first we're going to take those percents and turn them into masses and line them up along the far left. Because remember, your percent is the relative masses, and that's what we need, just the relative masses. And in step 1, we're going to convert those masses into moles. So using the molar mass of copper, again, I get this off the periodic table. I get the number of moles of copper. Using the molar mass of iron, again, I get this off the periodic table. I get the number of moles of iron. Molar mass of sulfur, I get the number of moles of sulfur. Okay, there's step one, converting our masses into moles, which is the atom ratio. It's just not whole numbers. So step 2a, we divide each of these by a smaller number at 0.245. And in doing so, of course, we get 1 copper, 1 iron, and it turns out we get 2 sulfurs. Since these are already whole numbers, they become our subscripts, our atom ratio, and the chemical formula. So there's the empirical formula of chalcopyrite. Okay, combustion analysis is one way of determining the formula of an organic compound, since we burn it and then determine how much carbon dioxide and how much water was collected. Okay, so combustion analysis of 2.4 grams of toluene yield 8.023 grams of carbon dioxide and 1.877 grams of water. What is the empirical formula? For the most part, this is going to look the same as what we've done before. The only difference is, once we get the number of moles of carbon dioxide, that's really giving us the number of moles of carbon. And once we get the number of moles of water, it's giving us the number of moles of hydrogen. And of course that 2 sitting out front because there are 2 hydrogens per each mole of water. So that's the only thing that's a little bit different. Now our normal step 2a, we're going to divide both by the smaller number. So we divide by the 0.1823 moles to get 1 carbon. And 1.143 hydrogen. Shall I just say that's pretty close to 1? Well, that's 14% off of 1. So I want to identify what type of fraction is that. Many of your calculators, and you may know how to use yours, you can put that on your calculator and determine what fraction it is. What I do is I would just take 1 and divide by 0.143, and that gives me 7. Excuse me, that gives me 7. And so I multiply, that's essentially telling me I have 8/7, and so I'm going to multiply the whole equation by 7 now, and that says that toluene has 7 carbons and 8 hydrogens for a formula of C7H8. Okay, we're told an oxide of nitrogen contains 63.1% oxygen and has a molar mass of 76 grams per mole. What is the molecular formula for this compound? Well, since they gave us the molar mass of the actual compound, we can determine the actual formula. But it all begins with the empirical formula. And so if we had 63.1% oxygen, then that other 36.9% must have been the nitrogen. Step 1, still step 1, convert these masses into moles using the molar mass of each. So again, step 1, using the molar mass, convert grams of oxygen to moles of oxygen, and grams of nitrogen to moles of nitrogen. I told you going back and forth between grams and moles is our most common calculation in all chemistry. And our normal step 2a, divide each by the smaller number. And when I divide 3.94 by the 2.64, I get 1.49 oxygens. And of course, when you divide 2.64 by 2.64, we get 1 nitrogen. So that 1.49 is really close to 1.5. In other words, that's really about the same as 3/2. So I multiply by that denominator, the 2 and 3/2, or 3 oxygens and 2 nitrogens. Put the formula into O3. And don't worry about what order you write everything in. It's usually metal before non-metal, or less electronegative before more electronegative, and we haven't talked about electronegativity yet. Okay, we're not quite done because we want to identify what is the molar mass of that dinitrogen trioxide. And when we add up the mass contribution of the nitrogen and the oxygen, we get that 76 grams per mole. So this is the actual formula. Okay, when propane undergoes complete combustion, the products are carbon dioxide and water. And one has to balance the reaction. And again, any combustion reaction, we let oxygen be last. So we start with carbon. 3 on the left, 1 on the right. What's your least common multiple? 3. So how many goes on both sides? 3. Then hydrogen, 8 on the left, 2 on the right. What's your least common multiple? 8. So how many hydrogens go on both sides? 8. And now we're going to count the oxygens on the right and hope it's an even number, but even or odd, we're going to force the O2 to balance. Okay, starting with carbon dioxide, we add 3 times 2 for 6. In the water we have 4 more, so that's 10. Yay, that's an even number. So 5 O2s. And we're done. We can double check. 3 carbons, 3 carbons, 8 hydrogens, 8 hydrogens, 10 oxygens, 10 oxygens. Okay, the catalytic conversion of ammonia to nitric oxide is the first step in a 3-step process which ultimately results in nitric acid. Let's balance this equation. Okay, again, oxygen looks like should be left for last, and let's start with nitrogen. 1 on the left, 1 on the right. Least common multiple is 1, so there's 1 nitrogen on both sides. Then hydrogen, 3 on the left, 2 on the right. 6 is the least common multiple, so let's put 6 hydrogens on both sides. And now let's count oxygens on the right, and I see 1 and 3 more for 4. So let me put 4 oxygens on the left. Oh, what happened here? Oh, I changed my coefficient for the ammonia. So I had to change my coefficient for the nitrogens. And now 5 oxygens on the right and 2 on the left. So like we did before, we're going to force that oxygen to balance. And then clear the whole equation by multiplying by 2. So 2 ammonias, 2 times 2 for 4 ammonias, react with 5 O2s to form 4 nitrogen monoxides and 6 dihydrogen oxides. Okay, I better double check this one. 4 nitrogens on the left, 4 on the right. 12 hydrogens on the left, 12 on the right. 10 oxygens on the left and 10 on the right. Hydrazine is a fuel used to power rocket engines. It's quite explosive, and a product is a byproduct in a reaction between ammonia and bleach, where it has to balance the equation for the reaction. Okay, well, anybody we should leave for last? And let's see, well, maybe the chlorine, because there's nobody else that's all by themselves. Okay, so let's start with nitrogen. 1 on the left and 2 on the right. Well, you know, I also see 2 sources of hydrogen on the right, so I'll probably let hydrogen be towards the end. Okay, so back to nitrogen. 1 on the left, 2 on the right. Least common multiple is 2. So there's 2 nitrogens on both sides. Then oxygen. I have 1 on the left and 1 on the right. Let me put a coefficient of 1 in front of each of those. And now hydrogen. I've got 2 times 3 for 6 on the left, and then there's 4 and 2 more for 6 on the right. And then I have 1 chlorine on the left, let me put 1 on the right. And do note, it's also charge balance. I have 1 negative on the left and 1 negative on the right. So we haven't really done much with this. Your balanced chemical equations also need to be charge balanced, and we'll see more of that later. Okay, that concludes this lecture where we covered 3.3 and a good chunk of 3.4, where we talked about the mass relations in chemical formulas. That introduced us to empirical formulas, their calculations, the relationship to actual formulas. Most of the time empirical formulas are actual formulas, but not always. And then we saw the relationship of elements in a chemical reaction. We talked about balancing chemical equations. We learned to balance them, did a few practice problems, and that's where we left off. And we'll talk more about mass relations in chemical reactions in our next lecture.